Hello, welcome to Dr. Nakamura's lecture series on bridge engineering, number A-6. Chapter 8, Composite Girder Bridges. When the RC slab is used as a deck of the plate girder bridge, it is connected to the girder with steel bars welded to the upper flange to prevent falling off from the slab, as shown in A. As the rebar is not strong enough to resist the shear force between the girder and the slab, a slip occurs as shown B. So it is designed that only the girder resists the bending moments, neglecting the contribution of the slab concrete. This is called non-composite girder. When the slab is connected with the girder by studs or rigid dowel, as shown in C, it has sufficient strength to resist the shear force, and the RC slab and the girder behave as a one piece, as shown D. This is called composite girder. 8.2 Design of composite girders. There are several points we have to consider to design composite girders. A. Young's modulus. The composite girder consists of two different materials, steel and concrete. The Young's modulus of steel, ES, is much larger than that of concrete, EC. The ratio of the Young's modulus, N equal ES over EC, is assumed to be 7 in the stress calculation. B. Design layers. The steel girder is erected first, and the RC slab is then casted. After the slab concrete hardens, curbs and pavements are installed. Then the bridge is completed and open for traffic. Concrete does not get strength before it is hardened. Therefore, the bending moments caused by the dead loads, such as self-weight of steel girders and RC slab, are taken only by the steel girder. This dead load is called pre-composite dead load. On the other hand, self-weight of curbs and pavements are taken by the composite section, which is called post-composite dead load. Live loads are taken by the composite section. The stress distributions due to the pre-composite dead load, the post-composite dead load, and the live load are shown here. For the pre-composite dead load, the stress at the upper and lower edge is calculated only for the steel girder. For the post-composite dead load and the live load, the stress is calculated for the composite section. The ratio of Young's modulus, N equals 7, must be included in the stress of the concrete slab. 8.2.2 Verification method of the composite girder. The steel section and the composite section are verified so that the stresses must satisfy the limit state 3. For the tension side of the steel girder, the stress consists of pre- and post-composite dead load and live load, which must be within the limit value. For the compression side of the steel girder, both erection stage and completed stage must be verified. 8.5 is for the erection stage and 8.6 for the completed stage. Lateral buckling and local buckling of the girder must be considered. For the compression side of the concrete, post-composite dead load and the live load are considered. The limit value of concrete is 10 Newton per square millimeters for the concrete with compressive strength of 27 Newton per square millimeters. Example 8.1 Verification of a composite girder. Taking a simply supported composite girder with a span length of 30 meters with a cross-section in this figure. Verify this composite girder. The dimension of this bridge is the same as that of the plate girder bridge shown in example 7.4. The grade of steel is ASM 490, tensile strength of 490 megapascal, and the compressive strength of concrete is 27 megapascal. Let's calculate sectional property of the steel section, which consists of the upper flange, web, and the lower flange. The section is not symmetric, so we have to find the position of the neutral axis. At first, the neutral axis is assumed at the web center. Then the eccentricity ES from the actual neutral axis is obtained by AY over A. YU, YL, moment of inertia, IS, are obtained like this. Sectional properties of the composite section, which consists of the slab, upper flange, web, and the lower flange. The concrete section is replaced by the steel. Therefore, cross-sectional area A must be divided by N of 7. The section is not symmetric, so we have to find the position of the neutral axis. At first, the neutral axis is assumed at the web center. Then the eccentricity EV from the actual neutral axis is obtained by AY over A. YCU, YU, YL, the moment of inertia IV, are obtained like this. The stress distribution is shown in this figure. The stress of the steel girder due to the pre-composite dead load is calculated with the design bending moment, moment of inertia, and YU and YL like this. The stress of the composite section, namely the steel section and the RC slab, due to the post-composite dead load and the live load, is calculated by these equations. For the stress calculation of concrete, the Young's modulus ratio N should be included. Next, the assumed section is verified. For the tension side of the steel girder, the stress consists of the pre- and post-composite dead load and the live load. It is within the limit value and satisfies the limit state 3. For the compression side of the steel girder, first erection stage is checked. The pre-composite dead load is applied and only the steel girder resists. The limit value should include the effects of lateral and plate buckling. In addition, the completed stage is checked. D1, D2, and L are applied, which was resisted by the composite girder. It satisfies the limit state 3. For the compression side of the concrete, the post-composite dead load and the live load are applied. As the compressive strength of concrete is 27 Newton per square millimeters, the limit value is 10 Newton per square millimeters. It satisfies the limit state 3. 8.2.3 Shear connector. The steel girder and the RC slab are connected by the shear connector. The stud shown in this photo is most commonly used as a shear connector. The limit value of shear of a stud is specified for the limit state 1, as shown in these equations. It depends on the height and diameter of a stud. Conventionally, the steel concrete composite girder is applied to a simple girder. In recent years, the continuous composite girder is sometimes adopted. In this case, at the span center, bending moment is positive and the RC slab is in compression, which is the same as the simple girder. However, at the intermediate support, bending moment is negative and the RC slab in tension and does not contribute. To solve this problem, it is effective to install compression forces or negative bending moment at the support, such as the pre-stressing with PC cables and jack up and down at the intermediate support. That's all for this lecture. See you next lecture.